Hi everybody, welcome to my 6th beam video. In this video I'm going to be solving the problem you see here of this beam with an applied load here, and you got some sort of hinge there, and I'm going to find the shear force and the bending moment diagrams. If you want to see another beam example or learn something else about mechanics of materials, feel free to check out any of my other videos. So the first thing I've noticed, of course, in this problem is going to be this sort of pin thing in there, alright? What does that do? Well, it allows a shear force to pass, but not a bending moment. Alright? And this totally makes sense. Because if you have a pin, alright, it's just going to be free to rotate at that point. But if you pass a force through that point, alright, it's going to resist. So that's basically what a pin does. And it basically lowers the degree of indeterminacy by 1 as well. Because if you check it out, we've got 3 supports. And if we only had 3 supports and no pin, we would have 3 reactions and only forces and moments equations to find them out. So we couldn't find them out using, the traditional forces method. So we have to do something about this sort of pin here, and I'll show you how to deal with that. But first, let's just do like we always do. We do a beam problem and do an overall free body diagram. Alright, there we go. Got it all drawn in, got our sign conventions, so people know what we're talking about. Now what's the magnitude of this load here? Well, that's basically the magnitude of this whole distributed load. So in our case, 20 kilonewtons per meter times 4 meters, that's 80 kilonewtons. So go ahead and write 80 in there. And we're just going to assume that the distances are all from up here. I'm not going to keep on drawing them in. So let's just do, like we always do, sum of forces. Alright, there we go. So we did sum of forces. Now, if we want to know something else about equilibrium, we can go to sum of moments. So let's do that. We'll do about this point here, which I called 1. I'm going to label these here 1, 2, and 3, just to give the reactions a name. Alright, and there we have it, our second equilibrium equation. Now notice here we have 2 equations, 3 unknowns. And this is where we need to take a special look at this pin. So for the equilibrium of some sort of body, or beam in our case, if the whole thing is in equilibrium, that means every piece must be in equilibrium. Let's take a look at just this piece here, from the hinge to this piece, and get a free body diagram of that. Alright, now, what goes here is important. It has to do with the definition of a hinge. We said a hinge could transmit a shear force, but not a bending moment. So if we cut it exactly at the hinge, we say there's some shear force V, but no bending moment. I'm not going to draw that little bending moment in. Okay? And under the length of this thing is going to be exactly 2 meters. So then, if we take sum of moments about this joint or about the pin, then we don't need to find out what that shear force is. We can say alright, so I've drawn it out here, and I've got my equations of equilibrium of moments ready to go. Okay, so this little bit of force here is going to be 20 kilonewtons per meter times the distance of this piece. That's just 2 meters, so that's 40 kilonewtons. And now if we sum up the moments around V, we can say R1 is 20 kilonewtons. Alright, and then we go 3 equations. Now this one doesn't explicitly mention, R2 and R3, but we can plug it into here, and we have 2 equations, 2 unknowns. So of course you can solve this sort of system equations any way you want, but I happen to like linear algebra, so I'm going to solve it that way. So I'm going to set up a matrix that has the 3 unknowns. And then you can row reduce it and you get the following matrix. Or, reading this out of the matrix, taking that this column still apply, we can say alright, there we go. I just like doing linear algebra. Keeps me from making substitution mistakes, because I'm pretty bad at making substitution mistakes. Alright, so now that we've got all the reactions, really there's not more of anything new that you need to know if you know already how to make a bending moment shear force diagram. But let's just go through and plot it, and you will see, or we'll find out, that the shear force does indeed equal 0 here. Alright, you don't need to be worried about it that it won't when you go to plot it, because you said it would be 0 when you define this equation. So if it doesn't come out to be 0 in your final bending moment, you've done something funny along the way. So how many different cuts are we going to need in this beam now? Alright, you might think you need a cut here, and then, oh, hinge here again. But really you don't need to do that. Alright, because the equations that we developed apply across this whole thing. You don't need to take into account the hinge. So we'll make a cut, let's say right here. And then on the other side of this hinge here. And here. Alright, let's get into some free body diagrams of this. Alright, so just a quick explanation here. Well, here I just quickly did some algebra, summed up these forces. But when I like to do the sum of the moments, when I make a cut, take the moments about the point that you cut. That way you won't need to include V in your moment equation. Alright, so if you did sum of moments around here, you would need to include V, and you had just found V here. So if you made a mistake here, that error will propagate into here. So just to be safe, take your moments about the cut point. Alright, and this force is 20x, right? 20 kilonewtons per meter times the number of meters. And then the distance it acts, well, it's a square distribution, so it acts halfway through. So moving on to the second free body diagram. Alright, so let's get some dimensions in here, because in the next case it's going to start to be important. Alright, again I'm measuring x from the newest point here. You could take it to be the whole piece, but I like to do it this way. And it makes it so later when I plot it, I can pretend that my Cartesian coordinate base, if you will start right at my cut. So it makes it easier to draw the bending moment diagrams and the shear force diagrams later on. So once again, summing up the forces, summing up the moments. Alright, there we go. And then the final step, of course, would be the third free body diagram of the piece looking the other way. Alright, now what's the distance of this? We can't just measure it in terms of x, alright, because it's not of length x, because x is measured from some point up to the cut. What we do, since we're analyzing just this piece here, we take x to start right at where the cut is, and then let it run out, and then this leftover piece would just be 1 minus x. Alright, so that's what it is in our case. And then again, sum of forces, sum of moments. Alright, there we have it, all the information we need. Now let's get into plotting it. So first what I'll do, let's quickly redraw the beam and draw our axes for each one. Alright, and V of course being for shear and M being for bending moment. Alright, so let's get ahead and plot this. So the first bending moment here, negative 20 x plus 20. So when x equals 0 up here at 20. And then, you know, it drops all the way down, negative 60. Alright, so x equals 0 at 1 meter away from the base. This will come in again later. Alright, so what's the shear force in the next section? Well, that's just V2. We develop that up here. Oh, it's just 45 kilonewtons. So that brings us about up here somewhere. Alright, that's not surprising because when we're here, we were kicked up this much, or bumped up that much by the magnitude of the reaction. And the reaction at 2 was 105. Alright, so now we've had that 100 kilonewtons, boom, that pushes us all the way down to, well, negative 55 kilonewtons. Alright, so let's go ahead and now plot the bending moment diagram. So M1 is this, x equals 0, it's 0. Now since V is the derivative of M, when V is 0, we have the maximum or minimum value. In this case, the maximum value right here turns out to be the maximum value. Then we sink down again. Alright, and if you solve it mathematically, the point where the bending moment equals 0 is x equals 2. Surprise, surprise, that's exactly where our hinge was. Exactly where the bending moment should be 0 because we defined it to be 0. So M2, negative 80 plus 45x. So this was negative 80. And then M3 starts us off at 55, and after 1 meter, we're brought back down again to the origin here. Alright, so that's how you analyze a beam with a pin in it. So once again, let's just notice the relationship here that, okay, because here we had a negative slope, quadratic, constant, constant. The value of the slopes here, I mean like the magnitude of the slope here is equal to what this here is. Alright, thanks so much for watching guys, and I hope to help you out. I'll see you in my next video on beams.